title is on attractors of Fibonacci maps.
Hello everyone, thank you for those organizers for giving me this opportunity to give this talk. So I will talk about attractors of specific type of maps called Fibonacci maps. So first, let me remind briefly what we mean by attractors. So this is one of the key objects in dynamical systems, and there are various notions of attractors. We will talk about cases when different notions actually give the same result. So assume we have a map from topological space to itself for a point x, we denote by omega of x, its omega leading set. And for a subset C of x, denoted by B of C, it's a basis of attraction. That is the set of point x for which the omega limit set of x is a subset of C. Also, we assume that there is a measure mu of on x. Then, so there are two standard notions: topological, a subset C of x is called topological attractor. If B of C is a residual set, the basis of attraction of C is residual, and C is minimal in certain sense with respect to this property. That is, there are no proper subsets of C which are also have this property. And the set is called logic attractor if B of C has a positive measure.
Residual where? In X?
In X, yes.
So there is only one attractor in this case?
Well, yeah, we assume in the systems where we will consider that there will be one topological attractor, but in general, you're right, there can be several disjoint subsets on which there could be various topological attractors.
But then usually they are not residual.
Well, yeah, residual is sort of subsets.
And this definition of Bayesian, it does not imply openness, right? Definition
Not necessarily, yes. Metric attractor, for instance, in our examples will be no vertex. So again, we assume that it's minimal with this property. So there are no proper immeasurable sense subsets of C for which we will have interesting case is when these two types of attractors are kind of perpendicular to each other, are disjoint. Namely, we will say that a metric attractor C is violent if it is not a topological attractor. Gentlemen should move
I move.
discuss one.
It's not good.
Ah, okay. Thank you. So just to get an idea, if we have a polynomial here T is polynomial, and the Julia set of this polynomial empty interior, but its the back measure is positive, then the Julia set will be example of a wild attractor. In this sense, because everything from the complement of the Julia set is attracted to infinity, the point of infinity on the Riemann sphere. But the points from the Julia set is an invariant closed set, so it satisfies the second condition. So this means that the Julia set in this case is a wild attractor. So such examples were constructed recently by.
So BC in this case is Julia set?
Yes. Yes, because Misha Lubitsch showed that almost all points from the Julia set are attracted to the omega Leibniz set of the critical points. So I guess it's not exactly the Julia set, but yes, modular zero measure, it's a Julia set. So there is a there is a subset in the Julia set which has a full measure inside the Julia set, which is attracted to the omega Leibniz set of the postcritical orbit. And since we don't care in the notion of metric attractor about zero measure set, then we can say that the Julia set is.
And how do you see minimality?
So let me check more accurate definition. Would be
still get positive measure.
Well, well, the omega limit set of the critical orbits is the only candidate from C. If you take, so for almost every point x, its omega limit set will be equal.
Ah, that's the point.
So at least in the quadratic case, I don't remember exactly what happens for high and 3D polynomials. That's maybe okay. So this was example, actually not very related to the rest of my talk. So in my talk I will be focusing on attractors of real dynamical systems. So the first example of real polynomials with a attractor. Were found by Bruin, Keller, Nowicki, and Strien in the paper in 1996. Among Fibonacci polynomials. So what are Fibonacci polynomials, or more generally, Fibonacci maps? A unimodal map f from some interval to itself is a Fibonacci map if the closest returns of the critical point to itself happen exactly Fibonacci numbers. So for any n, if we take so let u of n be nth Fibonacci number, so f u n of c minus c is less than f k of c minus c. For any k between 0 and u of n, or k between u of n and u of n plus 1. So what happens? So for instance, we have a polynomial, or more generally map of the form. So it is known that for any d greater or equal to 2, there exists a unique on CD, which is a Fibonacci map. And it's so we have a unique critical point at 0. What happens? So let CK be PD equals 0. Let me draw it closer to have more space. C1 is somewhere here. There are basically no conditions for C1. C2 is closer than C1 to 0. C3 is even closer, so that happens to go here under our map. Then from here go here. Then C4 will be further than C3. So we have so the next closest return will be C5, somewhere here. Then we will wander around. So C6, C7 will be further than C5, but C8 will be closer to the critical point. That's basically this picture of the dynamics of the critical orbit.
Excuse me, may I ask, because I couldn't decipher the general definition.
Yep.
So what is UN?
You have our Fibonacci numbers. So U1 equal to 1, U2 equal to 2, U of n plus 1 is U of n plus U of n minus 1. Next number is the sum of two radius.
And there on the right it's a K, FNC minus C is less than the FK of C, yes? What
Yes.
is-
Yes. So this tells us that UN's image of the critical point is, so it's closer to the critical point than all previous iterations. But also tells us that next time we will get closer only on U of n plus first iteration. Okay? So the closest returns of the critical point itself occur exactly at iterates of Fibonacci numbers. So Bruin, Keller, Nowicki, and Strien shows that so there exists a number, let's call it L1, such that for any d greater than L1, this Fibonacci map has a wild attractor. Namely, the omega limit coinciding with omega 0. But for a G delta dense set, V, we have that omega of V is a segment. So we have some segment around the origin. I think it's actually between points C1 and C2, on which we have kind of two different behaviors. For a positive measure of points, their omega limit set coincides with omega limit set of the origin, which is a Cantor set in this case. But for a residual, for a G delta dense set of points, we have orbits closed in the segment. Okay.
How are you able? I mean, are we supposed to understand this drawing? How are you able to? I mean, what is CD? I understand that.
Oh, sorry for the confusion. So I use the same letter C for the orbit, critical orbit, and for
so yeah, maybe that should be BD.
Yes. So let's change this maybe to KD. Here. So this drawing just illustrates the critical orbit, the first several iterates of the critical points, and here, yes, I need. Yes, so here it's a totally different constant. KD.
This picture is for what D?
For any. So this picture is illustrating the combinatoric of the critical orbits. It holds for any D.
Okay. It's not that we were supposed to calculate now and see that it's true. It just
No.
Okay.
It's illustrating the combinatorics of the critical orbit for Fibonacci
Using the
maps.
definition.
Yes. So there should be some additional minor condition about the position of the first point, but more or less using the definition you can figure out that this would be the combinatorics for assuming that have unimodal Fibonacci map. Okay. But until now there were no estimates on the degree D for which the Fibonacci map would have a wild attractor. So our result suggests that. So I'll explain in more detail what I mean by this later in the talk. So what are the numbers? So with the lowest D for which we were able to find a wild attractor is 5.8. much number. So what we did, we constructed an accurate computer-assisted scheme to study the attractor for particular D and to show rigorously that some maps do have well attractor, but other Fibonacci maps do not have.
But wait, if you know that 3.8 doesn't, so we know L1 is bigger than 3.8, but the fact that 5.1 has does not imply anything about.
Yes, yes. For now, we are not able to show that one can take L1 equal to 5.1. It's possible that after that there are no more. There are points where there are no wild attractors. But conjecturally, there is one point at which the transition occurred, so point before which there is no wild attractor, but after which there is wild attractor for all the degrees. Okay.
And is the point before 3.8 which has well attractor for
So
all
that we
points?
know, that we don't know either way. So this would be easier to study using a computer. One could subdivide segment from 2 to 3.8 into small segments, on each of which use precise approximation and show that there's no wild attractor, but the part starting say from 5.1 is infinite, and we don't know yet how to do this. And even the part before 3.8, it's computationally quite complex, so we aren't able to prove it yet. Okay, so there's one picture. So let me call this part 1. But there is another parallel way of studying Fibonacci maps using generalized normalization. So notice that Fibonacci maps are not renormalizable in the usual sense. Lubitsch in the paper showed that one can study dynamics of these Fibonacci maps using appropriate generalized renormalization. So what is generalized renormalization? So assume that we have a map F consisting of a pair of maps on two disjoint segments. To change the order, I think I used to assume that G is on G1. So here G1 is some segment AB, G1 is some segment alpha beta. So the picture would be like this. So we have -1, 1. So -1, 1 are just fixed segment. It can be actually any other segment. We fix it like this just for convenience. So there is some segment AB. For simplicity, we can assume that it's symmetric with respect to origin. And we assume that we have a picture like this. So F from P1 from -1 is unimodal with one critical point. Both boundary points of T1 are mapped into 1.
But wait, J1 was 80, right? So where is alpha and beta?
Sorry. Sorry for confusion. Alpha, beta are here, and AB will be somewhere here. So like this. Alpha, beta.
No,
it's
AB.
okay. AB. AB. Okay. This is our G, this is our F. So G from the segment J1 to -1, 1 is homomorphism. And the boundary points go to -1 and 1 respectively. So we consider such class of maps. So look at the real line like this. Here we have our segment T1 with the critical point x0 mapped onto segment -1, 1 unimodally. Here we have our segment G1, and the claim is that we can find smaller segment T2, which is mapped unimodally into G1 by the second iterate, and also smaller segment here J2, which is mapped by F one-to-one homomorphically onto the whole segment T1. So these are some basically first return maps onto T1. And in this case, we can consider now the new pair of maps which we have onto T and G2, which is called renormalization. So this pair of maps which we have now F respective to J2 and F respective to T2, which is the same as, so on J2 actually we have the map G, and so here F squared. F squared means first we apply F, then G. So this is called renormalization. So we start with a pair of maps F with this kind of structure, like this, and then we see on a smaller scale, after taking iterates, a pair of maps with the same structure. So this is usually denoted by F, and then.
But why would you say this is the same when there we see G applied to F? Because I understand.
So when we restrict this combination onto the smaller segment T2, this assumption implies, just to implies that we will be, so this will be a unimodal map into T1.
No, but because the assumption was about the critical point.
Yep.
Whereas here you said that the pair on T2 F squared behaves the same. So I don't know if it's the same. I don't know in what sense that is.
In the sense that we have this picture. So we have one central segment on which we have a unimodal map, and smaller segments, or another segment in which we have a homomorphism with this condition that the boundary points are set into the boundary points of a larger segment. So that's the idea. Now we're gonna rescale this appropriately, so that we once again have maps with images into -1, 1. So let's rescale Fibonacci maps defined previously with this is that which Milner showed that if we take say the Fibonacci polynomial which we defined before from the AD, we can restrict it to segments. So between certain points on the critical orbit, so just so for now just think that we can choose two segments appropriately, restrict the polynomial ED or Z to it, and then we can continue smoothly the resulting pair of maps to an infinitely
that sense.
Yes.
Here
Yes.
we didn't have any Fibonacci.
Yes, yes. So here the Fibonacci kind of encoded in the renormalizability. The fact that this pair of maps is infinitely normalizable, it can be transferred into the fact that the critical orbit of this pair of maps has Fibonacci combinatorics. So this is the relation.
That's a theorem, what you said.
Yes, yes. So Lubitsch and Miller showed that this is true.
But that's the other direction.
Oh,
Here
yeah.
you started with Fibonacci, you
Mhm.
got on, but you
Yes.
say that there is also a different theorem, if I understood correctly. If you start on this side,
Mm-hmm. Yes, yes. Well, it's not very hard just from using definition. So I skipped some details, not to bore you too much. So there are two possible choices of the segment G2, because the map is unimodal, so symmetrically there is another segment, but we choose the one which contains points from critical orbit, so some additional minor condition. And if a pair of maps is satisfying these conditions and infinitely normalizable, one can just, looking at the structure of infinitely normalizable maps, so we have a segment, here we have two segments, so that here we have the second iterate, here we have first iterate mapped homomorphically. If you look at smaller segment here, what happens on this segment? The corresponding iterate will be already, because we take composition G and F, so we take composition now of F2 and F. It will be only third iterate, and also another segment on which we have just the second iterate. When you go to smaller renormalization level, because of this rule, you will obtain now F.
in the addition, right?
Yes, yes, 2 plus 3, F fifths, and so on. So on the segment of prenormalization, your prenormalization will be F pair of maps F U of n, F U of n plus 1 for the Fibonacci numbers. Okay, basically pair M F is F U of n, F U of n plus 1, restricted to some intervals. Or something like that, maybe I'm off, but that's how the Fibonacci numbers appear. Okay. Now, when we have renormalization on some class of maps, to study properties of these maps, it's convenient to understand how this normalization acts, and typically it has fixed or periodic orbits around which it is hyperbolic. So there's a conjecture.
But wait, isn't it a problem that it's not results will you get that apply to the original map?
That's why I said that our results suggest. So we don't know exactly that the original map has a wild attractor. So we are working on that. Instead, what we can show is that there exist infinitely normalizable maps with critical points of degree d equal to 5.1, for which there is a wild attractor, and also there is infinitely normalizable map with a critical point of degree 3.8, for which there is no normalizable attractor. We are not able yet to prove the results for the whole class of Fibonacci maps, just for some.
But wait, for P or for some? Is it P 3.8 or is it in the
No.
sense that you started with P 3.8, you
Yes.
made a change?
Yes, in this sense. So more precisely, what we study periodic points of renormalization, so projection for any degree d greater than 2. There exists a unique period 2 periodic point periodic orbit fg of the Fibonacci renormalization. This sorry. So R is an operator in some class of maps, precisely when the map satisfies the conditions described above about the critical point. And the claim that there is so F and G are both pair of maps of this kind, and if we renormalize the first one, we obtain the second. If we renormalize the second, we obtain the first one. Okay.
But if that, because you know, the way you describe this operator R, you said there exists. And here you you treat it like that there is some uniqueness that I have, right? That I have some map and I want to use my operator R. There is no choice. Is that correct?
Yes, but if you have pair of maps G with conditions described before, then you can uniquely define the renormalization in this way. There is a unique choice of the segments G2 and G2,
Okay.
and there is a unique linear map standing appropriately T1 on the segment. So this is a well-defined operator with some class of maps. So the precise theorem which we show has a lot of self-similarity, linear self-similarity, and it allowed us to construct certain recursive scheme to study the attractors. So conjecturally, if we take corresponding Fibonacci polynomial, construct in this way smooth pair of maps, then when we apply renormalization operator to this pair of maps, in the limit we will obtain exactly this periodic point of period 2. And this would transfer property of corresponding attractors from periodic point to initial polynomial.
Okay, so first question, f and g,
Yeah.
these are two functions. When you say there is no right attractor, are you referring to both of them?
Yes. Yes. So they are related, just very simple change. So it's something like that. Mark if G is two periodic point for R and F is the pair GF, then capital G will be the pair minus GF. So periodic points, normalization acts very in very simple way. It just flips G, changes the rotation. And so the properties are the same. If one has one attractor than the other, and vice versa. Okay, so let me talk a little bit about the method of proof. So let's take some details. So let's start 3. equivalent. So we consider the sets which under some iterate land inside the ends renormalization interval. We also consider these sets inside the ends renormalization interval which escape and never return to it. Well, we also need some technical modification of this set. We so you need to understand the short one. It's some larger set containing yn, but actually not too much larger. So the picture is like that. So here we have a small interval of n simulation, some small interval around the origin, and xn is a set of points which land under some case iterate inside. So this is a point inside n. Yn are points which escape and never return. So we denote eta m as relative measure of xm inside the initial segment. So basically, eta m is a probability for a point inside our domain of definition, T1, to land under some iterate inside Tn. So probability is that we will come close to 0. And similarly, delta n is probability that we escape in some way and will never return in this small interval. So what we showed constructive dichotomy. For Fibonacci maps, there exists constant C depending on the degree of the critical point, such that exactly one of the following holds. case, eta n converges to 0 exponentially fast. And there is no wild attractor. Case 2. This ratio at the m of the time stays bounded from above and below. In this case, both these probabilities converge to 0. And there is no wild attractor. That is the basis of attraction of the post-critical orbit has 0 Quebec measure. And the final case, there exists m such that eta n over theta n is greater than c. In this case, infimum of eta n is positive. And the corresponding map from the periodic orbit conversation has wild attractor. And so let me formulate the key statement in the proof of this result. Key statement. There exists a constant c, it's the same constant here, such that for any n m one has that at we have certain recursive estimates which allow us to control these probabilities. So this is a key statement in the proof of this constructive theorem. So the idea briefly is the following. So assume we have some numbers n and m, and we want to obtain some results about this probability for n plus m. So here somewhere here we have Pn plus m lying inside T n, I think. We want to see how a point x can land inside T n plus m. So first we notice that the probability that this point will land under some interval inside Tn is exactly at the n. So there is a probability at the n to land here. After we land the first time, there are some options. One option is that we will land inside at n plus n quickly. And basically, because here we are going from nth level of renormalization to n plus mth level of renormalization, we can rescale this to the first level, and it will correspond to go m level down. So the probability of this happening is at the m. But also there is a probability that we will escape and never return. Sorry, I have not defined zeta and m. Zeta and m are the probabilities that we will escape before landing into n plus m level. Something like that. So if we did not have this option, then the probability would be just eta n times eta n, more or less. Because of this option, we have here the denominator plus c zeta n m. So this is a very basic idea. C here is because we have certain distortions of the derivative of the point on a small segment. Okay, so this was the idea, very rough, very sketchy, and actually also cheating idea of proving this Carson inequality. Then using this Carson inequality, playing with it around, we can prove this. For instance, if this part is true, what happens when we apply this inequality one time? So this part, this ratio is less than 1. So eta n plus m is less than eta n plus 1 times some constant gamma less than 1. When we iterate, we obtain exponential convergence, so we obtain this case. And what does this case tells us? It tells us that probability for a point coming arbitrarily close to 0 is actually 0. Because probabilities of coming to some small interval converge to 0. But this exactly means that probability that omega limit set of a point contains the critical point is 0, so this means that we don't have a valid factor. So this is just idea of the proof of the first part. Similarly, you can prove second and third. And then we have also computational part, estimating these constants, estimating eta n zeta n for a particular degree d, and also big computational part on computing actually the periodic points of renormalization. to start with. Um, and that's how we obtain our results on existing model attractors for d equal to 5.1 and non-existent for d equal to 3.8. We tested also some other numbers. These are just the closest numbers yet made. Okay, that's it. Thank you.
Thank you very much. Are there any questions? Maybe online?
I have a question.
Yep.
Can you? Yeah, you can hear me. Okay, that's good.
Yep.
At the beginning of your talk, you gave some conditions under which the Julia set of a polynomial is a wild attractor. And I wanted just to ask whether it is known, like what is the typical situation? For example, is it known that for a typical polynomial, the Julia set is not a wild attractor, or maybe the opposite, or maybe it's unknown?
So for typical polynomial, the Julia set has, well, in some sense, for typical has zero measure. For instance, for hyperbolic polynomials, it has zero measure. Björk, Lubish, and Davila constructed different types of examples of polynomials having positive area Julia sets, but the constructions are quite complicated, quite involved. So it's rather not typical to have.
Okay. So you really need to have some special construction to get it.
Yes. And actually, it is believed that it can be obtained for Fibonacci polynomials. So my belief is that for d equal to 6, the Fibonacci polynomial d power d plus kd, which we defined at the beginning, has positive area Julia set. So we plan to study this next with Denis. Moving from the real case to the complex case. So we hope to prove that all d for d equal to 6 will have a Julia set of positive contact measure.
Thank you.
So the way you are thinking about it, first you are testing it in the real case, you find this 5.1, now you take 6 bigger than 5.1, and then you say, I saw a wild attractor here, so probably there is a wild attractor in the complex.
Yeah,
and the mechanism. But do you know the other side? Because like your statement in the beginning, I guess, was you gave some conditions for a wild attractor. But if I tell you that the polynomial has a wild attractor in the complex sense, what can you conclude?
So I don't know if I can conclude anything about the real case in this case. So the relation is rather ad hoc. I don't know the direct relation.
Okay, any other questions? Well, if not, let's take Artem again.
Thank you.